Hey guys, today we are going to learn how to use the rational root theorem to solve equations with a degree greater than 2. So like this right here, x to the third power, where there's going to be 3 roots. How do I find those 3 roots? I can do that with the rational root theorem. But first, we need to make sure that we are brushed up on synthetic division and solving quadratic equations where the power here, the degree is 2. So to divide with synthetic division, I use this right here to find my number to put outside. So I'm going to use a negative 2. So I'm saying that x plus 2 is the factor, and I use the value of x that would make a 0 for this factor. So I use a negative 2 here. And then I put all of my coefficients here inside, and I make sure I put a 0 for any missing powers. So I have 1x to the 5th. I have no x to the 4th. Okay, I don't want to skip any descending powers. I have negative 7x cubed, negative 5x squared, 0x, and 3. Okay, now right here is where my remainder will go. Okay, so I start by bringing down the 1, and then I multiply and add over and over until I get to the end. So I multiply and get negative 2, add and get negative 2, multiply and get 4, add and get negative 3, multiply and I get 6, add and I get 1, multiply, negative 2, add, negative 2, multiply, 4, add, and I get 7. So here's my remainder, and I have a constant term, x, x squared, x cubed, and x to the 4th. So I have 1x to the 4th minus 2x cubed minus 3x squared plus 1x minus 2, and then I have a remainder of 7, so that's plus 7 over x plus 2. Okay, and next we are going to solve this quadratic using the quadratic formula. So x equals the opposite of b plus or minus square root of b squared minus 4 times a times c all over 2 times a. Okay, so I have 3 plus or minus, okay, and then we can use our calculator if we need it to evaluate what's underneath the radical. So I have negative 3 squared, which is 9, minus 4 times 2 times 5. So I have negative 31. So the square root of negative 31 all over 4. Okay, now there are no square numbers that go into 31, but this is the same as the square root of negative 1 times 31, and the square root of negative 1 is I. So I have 3 plus or minus I times the square root of 31 over 4. Hey, welcome back, guys. Today we are going to solve polynomial equations with a degree that is greater than 2. We're going to do that using the rational root theorem. And so first, we're going to find all of the possible rational roots. Then we're going to find which ones actually are roots. For some of these, the rational roots might be it. For some of them, we might only find some of the roots to be rational, and others are irrational. But we'll start with finding the number of rational roots, or all the different possible rational roots. And number 1, how many complex roots are there? Well, this is a third degree polynomial because it starts with x cubed. Therefore, there will be 3 complex roots. They might all be rational. They might all be real. They might not be real. So there's possibilities of different types of roots, but we're going to start with the rational roots. Okay, so here's how we begin to find these roots. We're going to find all the p's over q's. And what does that even mean? The The p's are all of the factors of that constant term. Q's are all the factors of the leading coefficient. So here the leading coefficient is 1. So Q is the positive and negative version of all the factors of 1, which means plus or minus 1. P is plus or minus all the factors of 21. 21 is divisible by 1, 3, 7, and 21. So all of the possible rational roots are all the p's over all the q's. So that's plus or minus 1 over 1, 3 over 1, 7 over 1, and 21 over 1. So these are the possible, I'm going to stress that, possible roots, possible rational roots. It doesn't mean they all are roots, but they're possible. Okay, so there's two different ways we can go from here. We could plug all of these numbers, positive 1 and negative 1, positive 3 and negative 3, 7 and 21, into this equation. And anything that gives me an output of 0 is an x-intercept, therefore it is a root. Or, if you have a graphing calculator, maybe a little bit easier, go to y equals and plug in the equation. So that's x cubed plus 5x squared minus 17x minus 21 and graph it. Okay, so I can see 3 real roots. It crosses the x-axis 3 times that I can see. Out of this list, positive or negative, any of these numbers, this one over here looks like it might be negative 7. So I'm going to trace negative 7, and it gives me an output of 0. So I know that one of the roots is negative 7. This one looks like maybe negative 1. So negative 1 also gives me an output of 0. So that's one of my roots. And that one looks like it's probably 3. So trace 3, I get an output of 0. Negative 7, negative 1, and 3. I said there were going to be 3 roots because it's a degree of 3. Those are my 3 roots. I found them all on the graph. This one here, number 2, is a degree of 4. So there will be 4 complex roots. Q is all the factors, positive or negative, of the lead coefficient, 7, so that's 1 and 7, goes into 7. P is plus or minus all the numbers that go into 30. 1, 2, 3, 5, 6, 10, 15, and 30 are all the numbers that go into 30. So there's 1 times 30, 2 times 15, 3 times 10, 5 times 6. Those are all the numbers that go into 30. So P over Q is plus or minus all the P's over all the Q's. So all these P's over 1 is 1, 2, 3, 5, 6, 10, 15, 30. And all the P's over 7. So that's 1/7, 2/7, 3/7, 5/7, 6/7, 10/7, 15/7, and 30/7. So all of those positive or negative versions are possible rational roots. So we go to the graph, And again, we can just plug in all these numbers, the positive and the negative version, to this equation. Anything that gives me an output of 0 is a root. But it'd be a little bit quicker just to put in the equation. You have a graphing calculator, 7x to the 4th plus 19x cubed minus 41x squared minus 95x plus 30. Okay, so there's my graph. All the way to the left here looks like maybe -3, so trace -3, and I do get an output of 0. Okay, so x equals -3 is one of the solutions. Okay, right here looks like somewhere around -2. But my output at -2 is not 0, so -2 is not correct. Any other fractions here that look like they could be -2? There's 10 sevenths, 15 sevenths. They could be somewhere in that range, so I could trace 10 sevenths, not an output of 0, 15 sevenths. And those should have been negative, so I'll try that again. -10 sevenths, not an output of 0. -15 sevenths, also not an output of 0, getting a little closer, but it's not 0. So it kind of looks like maybe I'm not going to find that one on the graph. Maybe this one right here, though. Try that, 2. Nope, that's not going to work either. We've also got one right in here that's kind of difficult to see. That's not even close to 1. Maybe 1/7. No. How about 2/7? 2/7 gives me an output of 0. Okay, so that's another root. Now, this one right here I wasn't able to find, which means I'm probably not going to be able to find the next one either. So here's what we can do. I've got 2 roots at -3 and 2/7. That means if I was to factor this, I would get x plus 3 as a factor, and x minus 2/7 as a factor, and something else. And I don't know what yet. But I can use synthetic division in order to find out what the other factors are. So here's what I can do. My factor is x plus 3, so I can use that root, -3. And I've got 7, 19, -41, -95, and 30. So I can bring down the 7 and multiply. -21, add, -2, multiply, add. So that's going to be -35. Multiply, and I'll get positive. So -3 times -35 is 105. Add, and I'm going to get 10. Multiply, -30. Add, and I get 0. Remainder 0 is very important. If I don't get a remainder of 0, I have a problem because I already said x plus 3 is a factor. So when I divide using a -3, I better get a remainder of 0. What this gives me is an x, or a constant x, x squared, and x cubed. I need to keep doing it until I get an x squared. So I'm going to divide again using 2/7. Okay, so I'm going to bring down that 7 and multiply, and I'm going to get 2, add, multiply, add, multiply. So 2 times -35 divided by 7. -35 divided by 7 is -5 times 2 is -10. And I get a remainder of 0. So I get 7x squared minus 35. and I'm going to set that equal to 0 and solve. So I'll move that negative 35 over. 7x squared equals 35. Divide by 7. X squared equals 5. Take a square root. X equals plus or minus the square root of 5. So my other two roots are the square root of 5 and the opposite of the square root of 5. Go ahead and pause the video and try the next problem. So this problem has a degree of 3, which means there are 3 complex roots. Okay, so now we need to find Q and P. So Q is all the factors of the lead coefficient, 2, which is 1 and 2. And P is all the factors of the constant term, which is also 2. Okay, so P over Q is plus or minus all, that should have been a P right there, all the P's over all the Q's. So 1 over 1 and 2. So 1 over 1 is 1. 1 over 2 is 1/2. Then 2 over both of these. So 2 over 1 is 2. 2 over 2 is 1, which is already listed, so I don't actually have to write that a second time. So there's my list of possible roots. So I can plug each one of these in, the positive and negative, into here. If I get 0 as an output, then that's a root. Or I can go to the graph. So we type in 2x cubed plus 9x squared plus 8x plus 2. Okay, so this one over here looks like somewhere close to -3, and I don't have anything quite like that. So that definitely won't work. Maybe right here, -1/2. So we'll trace -1/2 and see if that works. And it does. I get an output of 0. So one of my solutions is x equals -1/2. Okay, and I don't see anywhere else that I'm going to find one on that graph. So I'm going to use synthetic division. So I'll use -1/2 and all my coefficients, 2, 9, 8, and 2. So I bring down the 2 and then multiply and add until I get through the end here. So -1/2 times 2, -1, add, I get 8, multiply, -4, add, multiply, and add, and I get a remainder of 0, which is a must. If I don't, then I made a mistake somewhere. So I get 2x squared plus 8x plus 4. So we're going to set that equal to 0 and solve it. Let's solve this one with the quadratic formula. X equals opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Okay, so 8 squared minus 4 times 2 times 4. So that's 64 minus 8 times 4 is 32. So we've got a 32 here. all over 4. Okay, so any square numbers that go into 32, 16 comes to mind. So negative 8 plus or minus square root of 16 times 2 over 4, which is negative 8 plus or minus 16 square root is 4, so 4 root 2 over 4. And 4 goes into negative 8 and into 4. So I'm going to bring this over here since I've already kind of blocked off that space. So that's negative 2 plus or minus square root of 2. Okay, and that represents two answers, negative 2 plus the square root of 2 and negative 2 minus the square root of 2, a pair of conjugates here. Go ahead and pause the video and try this last one. So the last one has a degree of 4. So there will be 4 complex roots. Right, so the q's come from right here. Q is plus or minus everything that goes into 3, which is 1 and 3. And then P is plus or minus everything that goes into 6. 1, 2, 3, 6. So P over Q, all the P's over all the Q's. So all of these over 1. I got my plus or minus there. So everything over 1 is 1, 2, 3, 6. And then everything over 3. 1/3, 2/3, 3/3, which is 1, 6/3, which is 2, so I don't need to rewrite those. So that's my list. So back to our graph. So we're putting in 3x to the 4th minus 17x cubed plus 9 plus minus 3x squared minus 17x and minus 6. I started looking at the equation up above, so I better double check this. 3x to the 4th minus 17x cubed minus 3x squared minus 17x minus 6 should be good. So there's my graph. I only see 2 possibilities. Okay, so maybe 6 here. So trace 6. I get an output of 0. So 6 is one of my solutions. And then over here, it's not as far as negative 1. Could be negative 1/3 or negative 2/3. So let's try negative 1/3. And I get an output of 0 there. So negative 1/3 is one of my solutions. Okay? I need 2 more. So I'm going to have to use division. So I'll use the 6 first. It's always easier, nicer just to use the whole number first if there's a fraction also. Okay, so there's going to separate my remainder. I better get a 0 there or else I made a mistake. So we'll bring down the 3, multiply, add, multiply, add, multiply, add, multiply, and add, and I got a remainder of 0, so I'm good. I've got constant x, x squared, and x cubed. That's a problem. I need to get down to an x squared, so I've got to divide again. This time I'm going to use the negative 1/3. Bring down the 3, and multiply, add, multiply, add, multiply, and add. I got a remainder of 0 again. That's a good thing. So I've got 3x squared plus 0x plus 3. And I'm going to set that equal to 0 and solve. Okay, so I'm going to move this 3 over. 3x squared equals negative 3. Divide by 3, and I'll get x squared equals negative 1. Take a square root. X equals plus or minus the square root of negative 1. The square root of negative 1 is I, so I get plus or minus I. And that explains why I only saw 2 intersections here. There's only 2 real roots, which means 2 are non-real. I and the opposite of I are my remaining 2 roots. And so I can put a box around those 4 roots. Those are the solutions to my equation.